few words about him before he speaks. Paolo studied at Scuola Normale in Pisa under the supervisions of Riccardo Barbieri and then Riccardo Ratazzi for his PhD that he defended in 2003. Then he moved to Harvard as a postdoc. And since 2005, he has been a research scientist at the International Center for Theoretical Physics, or ICTP, in Trieste. He won several prizes from ENFN for his PhD, from the European Physical Society as a Young Physicist Prize in 2011. He's a very well-known figure in the field of theoretical cosmology and gravitation, with a very incredible number of high-impact papers on many subjects. So just to say a few, the effective field theory of inflation, also work at the interplay between dark energy and gravitational wave, about the shape of non-Gaussianities and the field of non-Gaussianities in general, and estimators for data analysis as well, about the CMB, also I found about baryogenesis, including also modified massive gravity. Well, actually he made pivotal contributions to many fields in theoretical cosmology and gravitation. So it's really a great pleasure to have him today. And so Paolo, the floor is yours.
Thank you. Thank you very much. It's a pleasure to be here. I will go through an introduction about the field of primordial non-Gaussianity. So I'm happy to take questions also during the talk, if any. And after giving an introduction, I will motivate the presence of a very important theoretical threshold in this field, which is not so far from what experiments will do in the near future. So I think it's a very important motivation for experimentalists to try to reach this important threshold, and I will explain why this is so important. So let me start from, if I can go to the second slide. Okay. So the setup is inflation. I remind you that inflation is, in general, is a period of accelerated expansion in the early universe. And we like inflation because a period of acceleration will make, for instance, the universe flat. So the curvature parameter will become small. So the universe will approach spatial flatness. And it also solves the horizon problem of standard FRW cosmology. How to realize this phase of accelerated expansion? Well, the simplest model is what is called slow roll inflation. And it's very simple. So you have a scalar field, which I call phi. And imagine that you have a potential of this form, and you are sitting somewhere where the potential is very flat. Now, a flat potential is approximately a cosmological constant. And a cosmological constant, we know that it leads to an accelerated expansion. Okay, so this is, of course, there are small deviation. Eventually, the field will get to the bottom, and this period of accelerated expansion will terminate. And this is the simplest setting for inflation. So in terms of an action, so you just have gravity and a scalar field with the kinetic term and the potential. In order to realize this phase of slow roll inflation, you need a very flat region of the potential. To be quantitative, you need some inequalities, which are usually expressed in terms of this slow roll parameter. So actually, you need a region in which the potential is flat. So you have a whole slew of inequalities that just tell you that the potential must be flat. Okay, and this will be important in a moment. Okay, this is a very nice story, but it's also a bit old-fashioned. Nowadays, we are not excited about inflation, not only because it solves this problem about hot Big Bang cosmology, but because of quantum mechanics. So when you turn on quantum mechanics, so h bar is different from zero, something very remarkable happened. And it's very easy to understand. Of course, the details are more complicated, but let me explain in very simple terms. So take the inflaton. So just to set up the notation, I'm going to describe scalar perturbations with this variable zeta. Of course, in general relativity, there is a choice of gauge, so you can use the fluctuation of the field or the fluctuation of the metric. So I chose this particular representation, but zeta will describe my scalar perturbations. I also want to say that I'm not going to talk about tensor modes, which of course are very exciting for other reasons, B modes and so on and so forth, but it's for another talk. So I will concentrate on scalar perturbations. Okay, so if I want to describe perturbations, I decompose my inflaton perturbations in terms of Fourier modes. Okay, and each Fourier mode is a simple harmonic oscillator. Okay. Okay, you can say, okay, it's very boring. Well, it's not so boring because if you write the action for this harmonic oscillator, so you can decompose this in Fourier modes. What is interesting is that you are in an expanding universe. This means that you have an harmonic oscillator, but the parameters of this harmonic oscillator depends on time because the scale factor is exponentially evolving. So the picture is that you have an harmonic oscillator, but this harmonic oscillator has time-dependent parameters. And so even if you are in the vacuum at the beginning, the fact that the universe expands change the parameters of this harmonic oscillator, and you find yourself in a state which is not the vacuum anymore. And this happens for each Fourier mode of the inflaton. Okay? So you have the wave function, and but the evolution of the universe make the potential change, and you find yourself in an excited state. What is remarkable is that we think that we are measuring this effect, which I stress is proportional to h bar, this is quantum mechanical, and we measured for instance, in the beautiful Planck map. So our understanding is that if I decompose this map in Fourier modes, maybe in spherical harmonics because I am on a sphere, but it doesn't matter. So our understanding is that these perturbations just come from the physics I described. So each Fourier mode is excited because in the early universe, although it was in the vacuum, the fact that there was a change in the parameters of the harmonic oscillator push it to an excited state, and this is what I measure in this map. So let me stress that this is an astonishing statement. So we should always be. So it's very remarkable. So we can do much better. Of course, we can. So I'm sure that you saw this plot. So what do I do in this plot? Well, I take Fourier modes of a given length or a given angular scale. And I plot, I measure the variance of each of these harmonic oscillators. And then I put it in this plot. Of course, you know that these oscillations, they have to do with the late universe because there is a plasma which oscillates. But of course, what is remarkable is that everything is fitting with the expectations, and it's really a measurement of these quantum fluctuations. Now, what is relevant is that already when I do this plot, I'm already doing an assumption because I'm plotting just the variance of each of these Fourier modes. And of course, when I do this, I'm already assuming that the statistics is Gaussian, in a sense that I'm already assuming that each Fourier mode is independent of the others. There is no correlation between this scale and this scale, for instance, and that the statistics of each Fourier mode can be described by a Gaussian statistic. Okay. So what about going beyond this? So why this is true? Why it's a good approximation? So can we, for instance, take the map and see whether there is a correlation among 3 points? Okay, something which is not described by Gaussian statistics. So a Gaussian statistics is just a two-point function. Now we are asking, okay, maybe there is a correlation among the three modes. And this is what is called the primordial non-Gaussianity. So non-Gaussianity in the primordial initial conditions of the universe. Okay, first of all, let's try to understand what do we expect. In the simplest model that I was describing, which is based on slow roll, I told you that in order to get inflation, you need these inequalities. Inequalities that just tell you that the inflaton potential must be very flat. And of course, think about, I don't know, an interaction 5 to the 4th. So this would be an interaction among 4 inflaton perturbations. But I told you that this must be very small because it's part of the potential. So there is this implication between slow roll, weak coupling, so the fact that, again, the potential must be very flat. And this, of course, implies Gaussianity. In other words, the fact that the potential is flat tells you that there is a limited interaction among different modes, and this is exactly what we call Gaussianity in terms of the map. If you want, it's very nice to be a bit more quantitative and to use the slow roll conditions, which are the conditions that allow inflation, to constrain, for instance, the quartic coupling of the inflaton. So you can do a bit of algebra, but what is so this 10 to minus 5 is the typical fluctuation in the CMB map. It turns out that this must be much smaller by many parameters compared to the square of this quantity, which is of order 10 to minus 9, 10 to minus 10. Okay? So the message is that the inflaton, in order to lead to inflation, must be very, very weakly coupled. If you compare this quartic coupling with the Higgs, so the Higgs, of course, is another scalar that we know very well and we are studying experimentally. Well, the quartic coupling of the Higgs is of order 0.1. So it's huge compared to what is allowed for the inflaton. Okay? So in this picture, the inflaton is very weakly coupled. So it's not surprising that we expect a very Gaussian statistics. Well, then you can ask, okay, so you told me about the theory. What about the experiment? So first of all, let me concentrate on the first deviation from Gaussianity, which is called the bispectrum, which is that the correlation among 3 Fourier modes, okay? And of course, there would be a delta function of conservation of momentum, which tells you that this triangle must close. And then there is a function B, which tells you the amount of the correlation among these 3 different modes. So first of all, this is a function of the triangle, so it's not a number. But let me postpone this discussion to later. Conventionally, the size of B is written in terms of these parameters, which are called F and L. But it's very important to remember that these numbers must be multiplied by 10 to minus 5 by the RMS of perturbations. So this bounds that come from Planck tells you that in the map there is no evidence of deviation from Gaussianity, and the bounds are extremely tight. They are of order few 10 to minus 5, maybe between 10 to minus 5 and 10 to minus 4, let's say. Okay, so this is super remarkable. So what we know experimentally is that our initial conditions that give rise to our universe are described by a Gaussian statistics, and that corrections must be smaller than 10 to minus 4. So this is the thing that in cosmology we know best. So we know something at order 10 to minus 4. Okay? So if we know something about our universe, we know that we are born very Gaussian. Okay? And this is, of course, due to the beautiful experimental results of Planck. Okay, so you can say, well, let's compare this with theory. Well, in the model that I was describing, so I told you that there is this logic that the inflaton potential must be very flat, but there is anyway a source of interaction in the game, which is gravity. Well, gravity is always there, and it's a nonlinear theory, so it will introduce some non-Gaussianities. These are very tiny. They were calculated by Maldassina 20 years ago. In this formalism, in this, so using this FNL, these will be of order epsilon or eta, of order slow roll. So these are of order, say, 10 to minus 2. Okay? So they're very far from the experimental sensitivity. So they are 10 to minus 2, while here we're talking about 5, or depending a bit on the shape, but we are very far from this bound. So I'm not going to talk about this. It's important to know that non-Gaussianities are not zero, but they are very tiny in the simplest model of inflation. So maybe in 20 years, I come back for another colloquium about getting here, I don't know. But this is small, so it's for the far future, maybe. On the other hand, what I want to do is to tell you that there are important motivation, theoretical motivation, to try to push these limits down to of order unity or below, if it's possible. Okay. The reason why maybe I should do that is that non-Gaussianities was very popular in the past. So this is Maldassina's paper in 2002. This is a paper about the shape, the possible dependence on the shape of the triangle of the function B. But you see that, okay, now it's a bit less fashionable. And the reason was, of course, that people were waiting for Planck results. Then the results didn't show any sign of non-Gaussianities. So people are not maybe so excited. So I feel that I need to motivate me and you again about this topic. I will motivate, as I said, trying to tell you that reaching a precision in which FNL is of order unity. Of course, later I will talk about the different shapes. So now I'm a bit vague. So for the time being, I'm just talking about the overall amplitude of the signal. Of course, experimentally, as we'll discuss, it's complicated. But so I want to convince you that getting to that threshold, even if we don't see anything, it will be very important. Okay. This is a nice threshold because there is no guarantee of anything, but it's nice to know that if we get to a certain point, we're going to learn something, no matter what is the result. Okay, this will be true both for the most popular shapes, which are called local and equilateral, as I will explain. So why this threshold is important? So I will try to motivate with few examples the fact that if I modify the simplest model of inflation and I get a qualitatively different model, I always produce something which exceed this threshold. Okay, so I mean it's not a theorem, so I will try to motivate with few examples and see if I convince you. Okay, so first of all, let me start with a couple of classic examples. So the first classic example, which actually I think it dates back to Francis and Jean-Philippe 20 years ago, is the possibility that so in the way I was describing inflation, the fluctuations of the inflaton are responsible to what we see in the sky. But actually, this is not mandatory. It could be that there is a second field, a second scalar field, whose perturbations are the source of what we see in the sky. Okay. So the idea is that during inflation, any light scalar field is excited. So it is enough that this second scalar at a certain point will play a role in the evolution of the universe. It may do different things. I don't want to enter into details. It may become important in the energy budget of the universe. This is what they call this curvaton. It may play a role during the inflaton decay. It could change some parameter of the cosmological evolution, okay? But it's not so relevant for what I'm going to say. The important point is that this field, the second field, sigma, plays a role sometimes in the evolution of the universe, okay? Now, so if the fluctuations of sigma play a role in the evolution of the universe, they will change the expansion of the universe at different points, okay? And this will give rise to fluctuations that we observe in the sky. The point is that when you do this calculation, and you evaluate how the universe evolves in different places with different value of this variable sigma, you find out that there is a relation between what you observe and sigma, which modulates these parameters. And in general, this relation is nonlinear, okay? And nonlinearities induce non-Gaussianities. And it's quite, of course, it's not a theorem, but I would say that it's quite general in this scenario that FNL local, I will come back to this later, is larger than unity, okay? It's not a theorem, but okay, it's very difficult to evade these bounds. You can easily generate something large, that is already ruled out experimentally, but it's very difficult to get below 1, at least in these models. Okay, this is one example. Second classic example is to remain with a single field, but to modify the inflaton Lagrangian. And the question here is, so the first question was, are you sure that it's the inflaton that generates the perturbations? It's not a second scalar field. Here the question is, what is the speed of the inflaton perturbations? Why the speed of the inflaton? Well, because during inflation, you have this time-evolving scalar field, which fixes a reference frame. So it's the reference frame in which the field is homogeneous. Okay. So since now you have a preferred reference frame, in general, you don't have a Lorentz invariance because, I mean, there is a preferred frame. And in general, the speed of the perturbations do not need to be the same as the speed of light. For instance, the CMB fluctuations, they have a speed which is the speed of a relativistic plasma, which is not 1. The same thing may happen for the inflaton. In order to see this in terms of an action, you need to modify the kinetic term. So this kinetic term is the relativistic ones and give a speed which is equal to unity. But if you write a more generic function of d phi squared, you generate a speed which is different from the speed of unity. Now, why this is related to non-Gaussianities? Well, because in some sense, in order to get a speed which is not the speed of light, you need to couple with the background, because the background is the one that breaks or chooses a preferred frame. And this can be written, I don't want to enter into details, is what is called the effective theory of inflation. But what is important in this slide is that you see the presence of a speed of propagation here, which is not unity. Pi here is the inflaton perturbations. So the CS also appear here and describe interactions, so cubic interaction of the inflaton. Interactions which are not the potential, because the potential, I told you, that is very constrained, but these are interactions which involve derivatives which do not spoil inflation. And you can check that the FNL parameter is given by this expression, which again is of order unity, is a bit below unity, unfortunately, times 1 over CS squared. So if CS is not unity, but it's, I don't know, 1/3, for instance, or even smaller, you see again some signal of non-Gaussianities, okay? So again, pushing these to become of order unity will tell us that CS must be very close to unity, okay? So this is another example of a modification that lead to non-Gaussianities. But these are the two classic examples. And now let me give two more examples, which are a bit more, let's say, recent, just for the experts. So another question that you can ask to inflation is, okay, you describe this story, but is it possible that the inflaton, as it moves, dissipates energy into some other form of energy? At the end, the whole energy of the universe is in this field which is moving, so it may transfer some energy to some other field. So this is a paper that we're working on, and the sector in which energy is transferred is called chi. So this is the inflaton Lagrangian. And now there is another scalar field which is called chi, which has mass terms, so it's a complex scalar field. And also it has a coupling with the inflaton given by this expression. So it's a coupling of the derivative of the inflaton to this thing. Now, I don't want to enter into details, but what is interesting is that if I look at chi, you're going to see that there is an instability. So if I take a chi wave and I go to later times, there is a period during which chi grows exponentially. Then this instability stops and it starts oscillating. So in other words, in this scenario, chi is produced by the motion of the inflaton. And so the inflaton is dissipating energy into this second field. For the experts, I will come back in a second, but this is not so different from what happens for gauge field when you have these kind of interactions. It's just for scalars in this case. And the difference compared to this case is that this instability is on scales which are much shorter than Hubble. Okay, so no details, but so dissipation, as you might expect, shows up in the inflaton perturbations. Now I call the inflaton perturbation var phi in this slide. So the dissipation of energy into chi shows up as a friction term, which adds to the Hubble friction. So there is an extra friction which is proportional to the dissipation. Okay. Also, so this is one of the effects of chi. There is a second effect that has to do with the fact that these chi perturbations, of course, they are produced and they also back react on the inflaton. Okay. So now the picture is a bit different from the usual one. So the picture is that it's not the quantum fluctuations of the inflaton that we see in the map, but are the chi fluctuations that back react on the inflaton and makes the inflaton perturbations. So this comes from this operator O, which is just the effect of chi back into the inflaton. Anyway, so also in this case, non-Gaussianities are always larger than unity. So for gamma large, you get this kind of expression. So it's for gamma large is larger than unity, but you can also check that even for small gamma, to the extent that the source of perturbation is chi and not the usual vacuum fluctuation of phi, non-Gaussianities are always larger than unity. Okay? So again, the message is if you have a model in which you have dissipation and the source of perturbations are these fluctuations in the chi sector, you also should see non-Gaussianities above the threshold that I was describing. Another example, another question that you can ask is, okay, you told me that there is the inflaton. Are you sure there is no radiation around on top of the inflaton? Well, the first reply is that, well, during inflation, the universe expands very quickly. So if there is radiation, it will be diluted away. Well, it will be diluted if the inflaton does not regenerate it as it evolves. So this is a scenario which is called warm inflation for obvious reasons. So it's inflation plus a thermal bath. So I said that this is new. Actually, this is very old. This is a very old idea. But I think that people were saying, okay, the idea is nice, but it looks very difficult because, you know, it's very difficult for the inflaton to have small interactions because you need to keep the inflaton flat and so on, but at the same time to be able to generate continuously these with this bath. So there's a tension between small couplings and the necessity to keep generating this thermal bath, which is diluted away by the expansion of the universe. It turns out that recently there was a nice, very minimal model that seems to have all the nice feature. For the experts, this is based on the coupling I was talking about, the coupling between the inflaton and the gauge fields, non-abelian gauge fields. So this coupling, as you might remember, is a bit strange, no? Because you remember that in the standard model, usually we don't put this coupling. So we put gluon, but not gluon tilde. So this tilde means the dual tensor, which is epsilon mu nu alpha beta times g alpha beta. The reason why we don't put this object which violates parity and CP, for instance, is because it's a total derivative. So it can be written as a derivative of something, and of course in the Lagrangian, a derivative does not play any role. Well, it's not really true because, so in the more advanced lectures about the standard model, you learn that this object has some topological effect. So even if it is a total derivative, it has, there are non-trivial gauge configurations which are still important, okay? And this is the reason why I don't want to enter into details, but it's a very peculiar operator. So being a total derivative does not kill what is called the shift symmetry. So does not affect the flatness of the inflaton potential. But at the same time, these topological transitions, so you should think about this gauge field jumping into different configurations, which are called, so these transitions are called sphalerons. So these are also relevant for when you discuss electroweak baryogenesis, so it's something that people studied. Anyway, the picture is that these transitions that you can induce, so that the inflaton is coupled to these transitions, and they induce a loss of energy from the inflaton to the bath of radiation of these gluons. And again, this loss of energy induces a friction similar to the previous case. Now, the difference here is that you form a thermal bath that thermalizes, but the idea of losing energy is similar to before. Anyway, to cut a long story short, there is a nice paper by Mirbabai and Gruzinov in which they study the non-Gaussianities in this model. So you have this is the inflaton, this is the fluid of radiation. There is a coupling between the two, which is induced by these sphalerons. And then there is this psi. Well, psi basically describes the thermal fluctuation of the system, okay? It has a certain two-point function, okay? But what is relevant for us is that you look at this plot, as a function of gamma over h, this FNL, well, you see that unless you are extremely unlucky and you sit in this window, FNL is always much larger than unity, okay? So again, if inflation is not cold, but it coexists with a thermal bath, you should see it with non-Gaussianities which are larger than unity. Okay. So I have two more examples very quickly, which are a bit more violent. So in the sense that, in a sense that well, let's see what. So violent in this sense. So one can ask a very fundamental question. So are you really sure that inflation is what you think it is? So in general, you think about inflation as again some clock, some field which is evolving in time. Okay. So the symmetries of the system is like this. So there is a time dependence, and of course translations and rotations are preserved. Okay, so it's a time-dependent system in which homogeneity and isotopy is preserved. But what about if you are very violent, you say, well, there are other symmetry patterns. For instance, this is the one of a solid. So if you think about this, if you want to describe a solid, so how do you describe a solid? Well, you describe the excitation of a solid in terms of three scalars that describe the motion of the particles from equilibrium, like in this picture. This is still a homogeneous system, but it's very different from this one. Okay, here homogeneity comes from some symmetries which plays with the scalar fields. Anyway, I don't want to enter into details, but what I want to say is that one can even consider models which are very, very different from usual ones. For instance, it is the model of solid inflation in this beautiful paper. And you see, non-Gaussianities are large, maybe even too large. Maybe this is already ruled out experimentally. We should enter into details, but it's 1 over epsilon, and epsilon is small, and CS for sure is smaller than unity, so this is much larger than unity. So again, if you really want to play with something very different from usual inflation, you get large non-Gaussianities larger than unity. The last example, well, one can be even more violent. One can say, okay, but are you really sure that it's inflation? Well, I don't know. People play with alternatives to inflation, and I think it's fair to say that none of these models is as simple and compelling as inflation. On the other hand, so I chose a model that I worked on just to give you so it's very different from inflation. The evolution of the universe so you start with a very low energy state, which is almost Minkowski in the very early past. Then you sort of generate the universe. That's why we call it genesis. And then there is reheating. But I mean, it's important. There is no exponential expansion like in inflation. It's very different. Okay? Now, then you can say, okay, how do I generate perturbations? Do I get perturbations which are almost scale invariant as in inflation? Well, it's not so easy, but you can do it. And the way to do it for the experts is that you play a trick, basically. So SO4, 1 for the experts is the isometry group of de Sitter. So it's so de Sitter is a good approximation for inflation, and the group of symmetries is given by this group. Now, in this scenario, these symmetries they're not the symmetries of the space-time, but basically they are the symmetries of your scalar system. And in some sense, let me put it this way, in this model, the scalar field feels like being in de Sitter for symmetry reasons, because we're basically using the same group. Okay. Let's keep the details, but what is important is that also in this class of models, you need to use a second field in order to produce perturbations. And I told you that if you use a second scalar field, you are going to generate local non-Gaussianities. Okay, so this falls into the first but I think this is a particular example, but I think it's pretty general that if you like modifications of inflation, it's very difficult to live without non-Gaussianities. Okay. So this is, okay, I gave many examples. I'm sure that there are many more, and for instance, Sebastian can give you more examples. But I think it's enough to make the point that pushing the bounds towards FNL of order unity is very important. So this is my cartoon. So we should be optimistic and try to push towards FNL of order unity. Now, in the next 15 minutes, let me enter a bit more into the details. In particular, I didn't talk about the shape of non-Gaussianities. So until now, I was talking only about the overall magnitude of the signal, but I want to tell you that there are, in a simplified way, there are at least two forms, two shapes of non-Gaussianities. There are many more, but at the very least, there are two classes which are important to stress. And the separation, which is also important experimentally, as I will comment in a second, is associated to this property, which is called single field consistency relation. And the idea is the following, that if you have a single field or a single relevant degree of freedom during inflation, for the same reason, you do not generate isocurvature. So you remember, if in order to generate isocurvature, which is the difference between different species, you need more than one field. Here, for the same reason, you can prove that the non-Gaussianity, the correlation among the three modes, become very small when one of the mode become very long in real space, so the Fourier mode go to zero compared to the others. So the logic, let me show you briefly, is that if you have a single field, everything is in the metric, so it is variable zeta, but you see the effect of a long mode on the other modes which are short is just a geometrical effect, which is, you see, it's something in front of the spatial metric, is something which rescales the short modes. But rescaling the short mode, it has to do with the tilt. So this is the tilt of the power spectrum. We know that we are close to scale invariance, so this result is very small. So without too many details, the statement is that if in all the models that I was describing, if you have a single scalar field, the non-Gaussianities are suppressed in this limit. So usually, again, there are many more, but just to guide you, usually one talks about two forms of non-Gaussianities. So this is the limit I was talking about, this squeeze limit in which one of the mode becomes much shorter in Fourier space than the others. So in the case of a local non-Gaussianities, this is very large, so it's large in this regime, while what they're called equilateral non-Gaussianities, they're very suppressed in the same limit. So just to simplify, this is a single field because it satisfies the consistency relation. This is typical of all the multi-field example I was describing. It turns out that this is not only a theoretical distinction, it's a robust distinction between single field and multi-field, but it turns out to be very relevant also experimentally. So let's get a bit closer to data. Of course, I'm a theorist, so I don't, so you should take my words with caution. So far, the limits on non-Gaussianity comes from the CMB. And just for the, I mean, the analysis is pretty straightforward. Okay, I don't want to So of course there are many details, but it's really very similar to, I have a map and I have a statistics and I want to see whether it fits a Gaussian, okay? So we really, so you know the CMB is very clean, so it's very easy to do this kind of analysis. Well, of course, very easy in quotation, but it's easier than, of course, when you try to apply the same methods to large-scale structures. Because in principle, also the distribution of galaxies is a good tool. So you can use these to constrain non-Gaussianities. And in the future, the promise is that these surveys will become more powerful than the CMB. At least they will contain more modes, so more information. Then whether it is possible to extract the information to go from this map to the map of the initial condition where I test non-Gaussianity, this may be a bit more challenging. So I just remind you that what we observe are galaxies, and the relation between the distribution of galaxies and the underlying matter distribution is challenging. But I chose a possible graph. I'm not an expert. There are many experiments. So I chose this particular graph. So here is the error on FNL for local non-Gaussianity and for equilateral non-Gaussianity in green. Forget about orthogonal because I didn't discuss about this. So this Planck is where we're now. So this is CMB stage 4. So a good improvement, but maybe not enough. Then there is some experiments. I chose these, but there are many more. But just to guide you the eye. So you see that for local non-Gaussianities, people are quite confident that we're going to go below this line, which is FNL of order unity. Okay. For equilateral, is much more challenging. So you see, we got here, so we are still not the order 1. Okay. Of course, this is this is the future. Let's say the next 10, 15 years. Then, of course, you can talk about even more futuristic things. But this is just to guide you, guide your eyes. Yes, as I said, the problem in using large-scale structured data is that the formation of structure is intrinsically very nonlinear. So when you write the continuity and the Euler equation to describe the formation of structure, these equations are nonlinear. Therefore, these nonlinearities will generate non-Gaussianities even starting from a Gaussian initial conditions. So in order to say something about the initial conditions, you need to control all these nonlinearities, not only these, but also the relation between the galaxy and the underlying matter, which is what is called the bias. So all these are nonlinear quantities, and I have to control each of them in order to be able to talk about primordial non-Gaussianities. So this, of course, is very challenging. There's a lot of work in this, and people are maybe getting more confident about what they can do. Let me conclude saying a few things about this contamination. So the message is that for local non-Gaussianity, the risk of being contaminated by the evolution of structure, which is nonlinear, is a bit less severe. And the reason is the following. I mean, of course, the formation of structure is very complicated, but it's not that everything can happen. In particular, we know very well that if I take a constant, this is the Newtonian potential, a constant Newtonian potential is something that I can just redefine away by a gauge transformation. And the same happens for a gradient of the Newtonian potential, which is just an acceleration, and we know that we can remove it by the equivalent principle. Okay, so this is what. It's the same logic that goes into the consistency relation that I was talking before. So this means that there is some observable which is very peculiar of primordial non-Gaussianities of the local kind, which cannot be mimicked or contaminated by the evolution of structure. Because if you go back to local non-Gaussianities, basically I use phi, but I could use zeta. So there is a quadratic piece which induces local non-Gaussianities. So this means that in the presence of this kind of non-Gaussianities, something peculiar happens, that when I look at a long mode like this, the power spectrum on short scales is modulated by the long wave. So here on the top, the power spectrum is larger. Here in the bottom, the power spectrum is smaller. So you see, this is a physical effect of phi. Okay, this has to do with the initial conditions, but this cannot be done by the evolution of structure, because in the evolution of structure, what matters are the gradients of phi, are the Laplacian of phi. So phi cannot have, is not physical, okay? So this effect, this effect gives what is called a scale-dependent bias, in the sense that, of course, in this region, you are going to form much more galaxies because the power spectrum is higher compared to here. But it's an effect which depends on phi, which cannot be contaminated by normal physics. So this is something which goes like 1 over k squared. So it's dominant when k goes to 0, so on very large scales. And this is something that people are quite confident in the sense, if I see something like this, for sure, it will not be due to my ignorance about the formation of structure. It must come from a primordial non-Gaussianity. And moreover, since I am in the squeeze limit, it must come from non-Gaussianities violating the consistency relation, that is to say, coming from a multi-field scenario. So this is a quite robust signal. So this is one of the reasons why people are more optimistic about the bounds on local non-Gaussianities, while for equilateral non-Gaussianities, this effect is absent and life is more complicated. This is the reason why there is a difference there. Okay, so I'm done. Just for the expert, I just want to mention 2 more slides about something that I'm doing at the moment, or some interesting problem for the future. So just to say that also theoretically, the field is still open. There are many questions to address. So in quantum field theory, we write a general Lagrangian in terms of operators. And in general, the operators, the coefficients of these operators are free function, okay? Are free coefficients. So. Now, it turns out that in the last 15 years or so, people realized that actually it's not always true that you are free to choose these parameters. There are constraints that come from analyticity. These are constraints that come if you assume that the theory has a standard UV completion. These are called the positivity bounds. Now, it turns out that one would like to apply the same bounds, so these are theoretical bounds, on the physics of inflation. Because, okay, it's good to have experiments, but it's also good to know that this is not possible because of theory. Okay. Well, at the moment, we are not able to apply this logic, for instance, to the effective theory of inflation. Okay. So this is something that I think is important, and it's something that should be done to add to the experimental bounds, also theory bounds of this sort. Last thing that I want to mention that I'm working on with also Sébastien is that I was only talking about the 3-point function. In general, one would like to study the full probability distribution, which will contain the 3-point function, the 4-point function, all the possible deviation from Gaussianity. And in particular, one may even be interested in looking at the tail of this distribution. For instance, if you're interested in the formation of primordial black holes, you might know that a primordial black hole form during inflation if there is a very unlikely fluctuation, which is not of order 10 to minus 5, but it's of order unity, so it forms a black hole. But when you're interested in this, you're looking at the tail of the distribution. But of course, as you go to the tail, you cannot expand the probability distribution with a small deviation from Gaussianity, because on the tail, the deviation from Gaussianity becomes very large. Now, it turns out that there is a method that can be used for unlikely fluctuations, which has to do with the semi-classical limit. You might remember that in quantum mechanics, the semi-classical limit is the limit h bar going to 0. Here, we're looking at fluctuations which are very large compared to the typical quantum fluctuation, which is of order h bar. So, looking at the tail of the distribution means the same as doing a semi-classical approximation. So there is some technique that can be applied to look at this region of the probability distribution, which might be relevant for some phenomenology. So this is something that goes beyond non-Gaussianities in the sense that it has to do with the full probability distribution, not only the 3-point function that I described at length in the talk. So I'm done. So I leave you with the questions that I was asking that can be answered once we reach a level of non-Gaussianities FNL of order unity. And so let's hope for the future. Thank you.
Questions, comments?
Thanks for your talk. Very interesting. I have a couple of bit silly questions, but when you mention dissipation or warm inflation, in both cases, you are modifying the Hubble, the effective Hubble scale in the equation for the derivations, right? You replace 3h by 3h plus gamma. Yes. And then, of course, you assume, because it's dissipation, that gamma is positive.
Yes.
Are there any cases, known cases, where gamma could become negative?
And not that I know. It's a good question, but I don't know.
Yeah, and then, sorry, I was just having this other silly question is Genesis model. So you're saying it's not an inflationary model, in the sense, but it's only in the sense that H is not constant. So yes, in a sense, it's hyperinflation. Like it's
exactly. It's a good. Thanks for asking, because I was a bit quick. It also depends on what is your definition of inflation. So what is pointing out is that if I look at this class of models, the difference is that it's good to call it hyperinflation, in the sense that during inflation, basically the energy density remains approximately constant. Here, the energy density is even increasing as a function of time. On the other hand, if you want, you can call it even inflation, because it's true that the universe is accelerating, but it's not only accelerating, but also the energy density increases. So in some sense, you can call it inflation. I would say that, well, if you want, it's a very, very strange kind of inflation. It's different qualitatively, but yeah, then it's a question of what is the definition of inflation.
Finally, if I may, just a very quick thing for this spell-dependent bias you referred to in your last book. Do you think it can be? Could you have active sources producing this kind of bias as well? Like cosmic strings or something like that?
I mean, I'm not particularly expert, but I don't think so, because this signal is dominated by the largest scale. In a sense, of course, at a certain point, going to very, very large scales has problem with contamination, with the mask, the survey geometry, and so on and so forth. But in general, this kind of effect induces a bias which grows as K goes to larger and larger scales, while I would expect that all the topological defects are not coherent over Hubble scale. But I don't know if somebody knows more, but yeah, I doubt that it's because this is it's a very peculiar effect. So it's an effect in which the very long mode that you observe in your survey, so there is this effect that the density of galaxies is higher or smaller depending on the position over a very long Weyland mode. I think it's very difficult to mimic, in the sense that it's clearly something that remembers about what happened during inflation when all these modes were inside the horizon. It's very difficult to imagine that there is some phenomenon which is coherent over a very, very long scale of order Hubble here and there and induce this effect. But okay, I'm not an expert of possible contamination.
Thank you for the very nice talk. Related to the dissipation mechanism, the coupling term that you showed was like a Chern-Simon coupling between the scalar and the electromagnetic.
Yes.
So this could cause birefringence of the CMB. I don't know if this is the case. And
very good. Yeah, it's a good question. Yes, the coupling that I was looking at is this. Yeah, just for the others. Ali is asking about. So the short answer is that no, in a sense that in order to have birefringence, you need the phi to be evolving after recombination. So in this model, phi is the inflaton, so it will get stabilized there. I don't know if maybe you can play and putting the two things together. Just to introduce birefringence, so if in the late universe you have a coupling of these with the photon, so now you need photon here. So here I was thinking about a non-abelian gauge. If phi dot is evolving, this induces an effect on the photons, which is what is called birefringence, that can be probed experimentally in the CMB, and it's very well studied. But yeah, these are two different things, because I'm playing with the early universe, and phi will disappear or become very heavy in the late universe, unless you want to join the two phenomena.
But I was actually related to the dissipation part. You have a chi also.
Yeah,
there's this instability. You're saying that the 5 F mu tilde.
Yes, so in this case, I'm talking about scalar, so there is no effect on gauge fields, so there is no...
This F mu...
You are referring to this?
Yes.
Yes. Sorry, this is not this model. The reason why I was mentioning this is because, sorry, I'm talking about the same coupling between this slide and the next. The difference is that in the next slide, I'm going to... So the model assumes that you have a thermalization of the gauge, the non-abelian gauge fields that you produce. Here, on the other hand, there is no thermalization, but it's the same coupling. So the reason why I was mentioning this is because this kind of instability that I described here happens in this class of models in a very similar way, with the only difference is that this window is at Hubble, while here it's well inside Hubble. But again, my answer is the same, in the sense that even in the case of dissipation, usually this phi, which is the inflaton, will become heavy and decay well before recombination, so it will not affect the evolution of photons from the CMB to us.
Okay, hi. I think you probably said this and I just missed it, but just for clarification. So you said that galaxy distribution contains more modes than CMB. Is that because you can prove smaller angular size scale?
Well, it's because of two things. It's mostly has to do with the fact that the CMB is a two-dimensional map. So, so I don't know, if you count the number of pixels in Planck or in the future, I don't know, you get something like 10 million pixels, which is the amount of information that you have. If we look at galaxies, is a three-dimensional object, and so people talk about number of modes that you can observe, which is more like 10 to the 9, 10 to the 10. So it's mostly this effect. Now, also, of course, this strongly depends on how much you can probe the short scales, as you were saying, and of course, so you really want to go to short scales because the number of modes grows as these to cube. But of course, as you go to more shorter scales, you are contaminated by the effect I was describing. So there is a tension. So I think the whole discussion is there. How much you can go to short scales? This is a lot of modes, but also a lot of troubles. So, yeah.
So if you want to make improvement from CMB side, then you go for smaller, finer angular side scales.
Yes, I think this is the reason why. Yes,
not
exactly.
the sensitivity direction. Side scale.
No, because the point is that the CMB, yeah, we need to go to shorter scales because the error on larger scales is not relevant because it's below cosmic variance. So the issue is to try to go to shorter scales. Of course, polarization can help. So basically, you have a second map. The combination of these two things is what give this improvement between Planck and stage 4.
Thank you.
Other question? Well, let's thanks Paolo for it.